Hello, everybody. This is your math techniques lesson. We're going to jump in with a quick introduction to the structure of the math section, and then we're going to head into some techniques for unpacking SAT standardized math questions. And then we will proceed to the kind of tips and tricks portion where we work on simplifying abstract problems by plugging in numbers or working off the answer choices, making them a little more concrete and easy to work with. So let's chat about the format. The format of the math section, there are 2 modules, each 35 minutes. Which gives you about 95 seconds per question because there are 22 questions in each of the modules. The first module, everybody gets the same, is nice and normal. The second module depends on the first module, and depending on how the first module went, you'll either get an easy or a hard second module. 75% of the questions are multiple choice with 4 answer choices, A, B, C, and D. 25% are what are called student-produced responses, which means you'll have to type in your own answer. For the student-produced responses, we have some very specific rules. If you ever forget what these rules are, please notice that on the left-hand side of any student-produced response on the SAT, it will remind you of all these things. So if you forget, just go give it a read. The reason I like to go over it now is so you don't have to waste your time on test day doing it. So if you find more than one correct answer, enter only one answer. It will be indicated in the question itself that there's more than one possible answer. It'll say, what's one possible answer? When they have that kind of language, be prepared to find more than one right answer. If that happens, just type in one of them. You can enter up to 5 characters for a positive answer and up to 6 characters for a negative answer, and the 6th character is for the negative sign. Characters are numbers and decimal points. We'll take a little closer look at that in a moment. If your answer is a fraction that doesn't fit in the provided space, you can reduce it or enter the decimal equivalent. If your answer is a decimal that doesn't fit in the provided space, enter it by truncating it, chopping it off at the 5th or 6th spot, or rounding to at the 4th digit. Any fewer digits is counted as incorrect. If your answer is a mixed number, such as 3.5, enter it as an improper fraction, 7/2, or as its decimal equivalent, 3.5. Do not enter any symbols such as percent signs, commas, or dollar signs. The only symbols you're going to want to put in there, well, it's not really a symbol, but is a decimal point. So let's talk a little bit about general strategy for the SAT. General strategy, you want to build it around the way that the SAT questions are built, right? You don't want to be responding to a test that's not the one that you're taking. So the first thing you're going to do is identify and highlight with your cursor what you're looking for. There's no option in the math section to actually do any real highlighting that's going to stay. But if you use your cursor, like, you're going to copy something and highlight it with your cursor, it will be blue and easier to see and remind you that you've looked at it. So very, very important that you check in with that first. Number 2, we're going to extract the information. This happens before you start to solve anything. You don't have to know how to solve a problem to extract the information. In fact, this is what allows you to know how to solve the problem, by really looking at what you have. So these first 2 steps are making sure you know what you want and what you have. If you're super clear about those 2 things, the way you're going to solve the problem will become a lot easier to see. If you are having trouble telling what you should do next in a problem, there's an excellent chance you don't know what you have or you don't know what you want. Be super clear about those 2 things, and the next steps will be easier. And again, once you do get to the solve-in, be sure to show your work. Be neat. For harder problems, they're longer. You're going to need to track your work, so make sure that you have a way of seeing what you've laid out for yourself. So let's give that a shot. And I give this one a read for us. A shipping service restricts the dimensions of the boxes it will ship for a certain type of service. The restriction states that for boxes shaped like a rectangular prism, the sum of the perimeter of the base of the box and the height of the box cannot exceed 130 inches. The perimeter of the base is determined using the length and the width of the box. If a box has a height of 60 inches and its length is 2.5 times the width, which inequality shows the allowable width X in inches of the box? Now, if you are a regular human, which I'm assuming you are, this was no help to you at all just to read it. There's no chance at all we are looking at this and thinking, oh man, the answer is C. No, probably not. What are we ready to do now? We're ready just to straight up read it again. Why? Because there's no way that we absorbed all that information. So let's bring in our technique right away. In fact, you don't have to read a problem all the way through and get stressed out before you start to implement good technique, okay? So remember, the first thing we're gonna do is identify what we're solving for and highlight it with our cursor. Oops, that's a little too big. Highlight it with our cursor. Which inequality shows the allowable width X in inches of the box? We're looking for the width of the box as X, yes? Now what we're gonna do is we're gonna turn off our brain cells. We're gonna put our brain in a lovely locale, maybe somewhere tropical, and we're just going to extract the information onto our scratch paper. I'm gonna do it here onto the screen. So the first sentence says, a shipping service restricts the dimensions of the box it will ship for a certain type of service. It's just fun facts, so we actually don't need to write anything down. You might notice that when they say it restricts the dimensions, that we might be looking at an inequality. The answer choices show us that too. It says the restriction states that for boxes shaped like a rectangular prism, which just means, a box, right? Kind of looks like that. If I could draw, it would look like that. There we go. The sum, okay, so sum means I'm adding, plus, of the perimeter of the base of the box. So I'm going to call that P, the perimeter of the base of the box. And what am I adding it to? The height of the box cannot exceed 130 inches. Cannot exceed means it can't go above. So the sum of the perimeter of the base of the box and the height of the box has to be less than or equal to 130. Cannot exceed, cannot go above, so it must be smaller than. Then it tells us that the perimeter, this guy right here, the perimeter is determined using the width and the length of the box. So if I am looking at, say, the base of the box, it's a rectangular prism. It has a width and it has a length. If I want to state the perimeter is the thing that's going along the outside of the box. It's this. So if I want to express it in terms of the length and the width, well, that's not the whole thing. I need two lengths and two widths. So let me express the perimeter in terms of the length and the widths. Two lengths plus two widths will give me the perimeter of the base of the box. Now, if I add that to the height, I know it cannot exceed 130 inches. I am just writing down what it told me to do. Then it says the height of the box is 60 inches. So take a look, the height of the box, that's right here. I think I'll go ahead and replace that with 60 inches. Why? Because they told me to. And then the next thing that they told me was that the length is 2.5 times the width. What? This length right here, the length that I made up and put in there, that thing there is 2.5 times the width, times multiplied, right? So let me just put that in for my L. I'll copy out the rest of it here too. And then it tells me that the width should be an X. Oh shoot, so let me go ahead and change my W's for X's. Okay, and now is something I want you to notice, what I call celebration station, when we have an equation with only one variable, and that variable is the thing that we wanted. Yay! So now what we can do is simplify and see if we can go at it. All right. If I multiply 2 times 2.5 in my calculator, I will get 5x plus 2x plus 60 is less than or equal to 130. I can simplify these guys. These are like terms. I can put them together. 2x's plus 5x's gives me 7x's plus 60 is less than or equal to 130. I'm going to subtract 60 from both sides because I'm trying to solve for my x. I'll get 7x is less than, boopity-boo, 70. We'll divide both sides by 7, and I'll get that x is less than or equal to 10. Now, when I look at my answer choices, nothing says exactly that, but the closest one that we have that in is going to be A. Now, the question we can ask ourselves is, where did that greater than 0 come from? Well, if our width is 0, then we don't actually have a box, and if it's less than 0, then we have a negative width, which would be very strange and not a thing that happens in the real world. So that's like kind of a real world restriction that we want to make sure we put in there. So we can see that when we're working on a problem like that, we actually didn't stop extracting the information until we got to about here. All this portion right here was stuff that they told us about in the question. We were just writing down what it says. Now, if you struggled a little bit with the extracting, maybe we forgot what a perimeter was, maybe we forgot what sum meant or something like that. But once we have all the terminology that we need firing on all cylinders, when they start to speak the language of the test, you'll be able to write it down in math. And again, taking it one piece by one piece, make sure that you don't miss anything. And again, look how well it guided us into a setup that will help us solve this question for what we're looking for. So keep an eye out that. Remember, identify what you're looking for, extract the information, show your work. Okay, now we're going to work on a skill called plug in. This skill helps you simplify abstract problems by replacing variables with something concrete, real numbers. So let's take a look at this one right here. If we were going to try this algebraically, we might do something like this. Bob has $4 more than Lisa does. So, okay, Bob is whatever Lisa is plus 4. If Lisa has X dollars, oh, they're telling me I should swap out my L for an X. How much, and I'm going to highlight this, how much would Bob have if he doubled his money? Okay, so we're thinking about this. We're like, okay, well, double means multiply by 2. So if I took Bob and I multiplied it by 2, I should take what Bob equals and multiply that by 2. I could say that 2 Bob then would indeed, if I distribute my 2, which we must remember to do, is 2x plus 8, which would be D. Now, algebraically, this one isn't too crazy, but on this test, you're also going to see problems like this one. If Leslie gives away K celery sticks, if Leslie gives away K celery sticks, she will have 1 over n times as many as she had originally. In terms of K and n, how many celery sticks did Leslie have originally? Now, even just to extract the information on this one, you might notice is a lot harder. So I'm like, I don't know, what do I do with that K? What do I do with that 1 over n? How do they relate together? Did they even give me an equation? It can be really tricky. So here's a thought. If we introduce a variable x for the thing that we're solving for, how much she had originally, we can now start to create an equation. So again, this might be a little tricky. The foreshadowing is that I'm about to show you how to completely avoid this, but this is the situation we might get ourselves into on the test that we're trying to avoid. So I'll show you the hot mess and then I'll show you how to get around it. So if we have X celery sticks, and we give away K, we might say I'm going to subtract away K of them, and then she will have, that means that will result in or yield or equals 1 over n times, multiplied by, as many as she had originally, which we decided was X. Now, if we're going to be super efficient about this, you must abide by Donna's rule of fractions, which is to clear them. We're going to multiply absolutely everything by 1 over n, so we can, or by n rather, to clear the 1 over n so we could solve for x. So what will that result in? Will result in nx minus kn equals x. Now, if I'm going to try to solve for x, you might notice that x is in multiple terms here. If I'm going to isolate x, and please pay attention to this very cool dance move, you will want to use it on the test. I'm going to isolate all the terms that have the variable that I'm looking for on one side and get everything else on the other side. So I'm going to isolate my x's on one side. I'm going to subtract x from both sides, and I'm going to add kn that doesn't have the x to the other side. So now when I simplify it, I get nx minus x equals kn. So you'll notice the x's that I'm trying to isolate are both on one side. And what I can do now when they're on one side is I can factor it out. And when I factor an x out, I'm left with, from this term, I'm left with n. And from this term, I'm left with 1, and they're being subtracted, equals kn. Now, if I'm going to isolate my x, how do I undo multiplication? Well, we do division. So we're going to divide away what I don't want, which is the n minus 1, because that's what's bothering my x right now. These will cancel out, and I'll be left with x equals kn over n minus 1, which is c. Holy actual heck. Yikes. That is not a fun amount of algebra to be popping a squat and doing in the middle of your test. So let's try something else. I'm going to get rid of this. And I'm going to go back to that easier problem. We're going to do a technique on that problem. Then I'm going to bring you back here and we're going to try it on the harder one. So, Bob and Lisa. Let's get rid of the algebra that we did. It wasn't too crazy, but I bet we can still avoid it because the idea here is, do we ever actually find out what x is? We never do, right? We never find out what x is. We never find out how much Bob has or Lisa has. Basically, they're giving us this unknown value for Lisa, asking us to base Bob off that, and then asking us to double that. So they're asking us to create a relationship to the unknown x, while it doesn't matter what that is. X is just a placeholder, and that's what algebra really is. It's putting in variables to hold the spot of something that could change, right? So Lisa could have $2 or $7 or $105. We're going to still end up with an expression that'll tell us how much money Bob has. Okay. So if that's the case and it doesn't actually matter what x is, it's just a placeholder, why don't we pop in something for x? Replace x with a real number, do the whole problem with that number, and then see the answers in relationship to that number. So the first step we're going to do is replace the x with a real number. I'm going to say avoid the numbers 1, 0, and -1. The reason for that is these numbers don't act like regular numbers. Yeah, when you square 1, it stays 1. When you square most other numbers, it changes, right? When you multiply anything by 0, it clears the entire term. Everything just turns to 0. This is going to hide certain things about the question. It won't make you get the wrong answers, but you're more likely to have multiple answer choices that appear to be the right answer. Listen, you can use 1, 0, and -1 cautiously later when you're kind of more experienced with this technique, but at first, just avoid those guys for now. Yes, let's do something simple like 2. I love 2. It's nice and simple, yes? Now we're going to do the entire problem as if x is 2. Bob has $4 more than Lisa has. If Lisa has $2, how much would Bob have if he doubled his money? Well, if Lisa has $2 and Bob has $4 more than Lisa does, then Bob would have 4 more than $2, which is $6. If he doubled his money, that would mean 6 times 2, that gives us 12. So the answer to our question in real numbers is 12. Now you might be thinking, but Donna, I don't see any answer choices that say 12. Fine. Take a look. Remember, we said that our x now is 2. So answer choice A isn't x plus 4, it's 2 plus 4. And that gives us 6, which indeed is not 12. So we know that's not our answer. Let's pop in a 2 for B. That would be 2 times our x, which is 2, which gives us 4. Well, that's not 12, so that's not our answer. This next one is 2 times 2 plus 4. Well, 2 times 2 is 4, plus 4 is 8. Well, that's not 12, so let's cross this out. This last one here is 2 times 2 plus 8. That's 12. And as you remember, that's our answer. So again, notice how we never had to set up an algebraic equation. We never had to go to Algebra Town to do this problem. What we did have to do was plug in a number that we were going to use instead of our variable, do the problem with real numbers so we knew what the answer choice should equal, and then plug in our variable to the answer choices to see which one gives us the same thing. Yes? Now, I want you to notice here I put a box around the number that I picked and a circle around the number that I'm looking for. And I'm going to say something really silly, and you're going to hear me say this 10 million thousand times, but in goes the box, out comes the circle. You really can't start this technique until you can say that, because the box thing goes in for your variable, and you'll know it's the right answer if that's what you get out when you plug in the box. So in goes the box, out comes the circle. All right, should we try this on that much harder question and see something really cool, which is no matter how hard the question, if you're using this technique, it will be nice and simple to work with. So let's think about picking numbers that make our life happy and easy, yeah? We don't get to pick everything in life, but this thing we do get to pick, so let's pick them nice, yeah? I'm looking at this fraction here. I already know that fractions aren't as comfortable as regular numbers, so I want to pick my most gentle fraction that I can think of, and I'm going to think about 1/2 for that. 1/2. Taking a half of something is easy, so I want to make my n equal to 2. So I'm going to write on my paper n equals 2. Will it work if I pick something else? Yes, absolutely, but it might make my life a little more difficult. So I'm going to pick that n equals 2 to keep my life simple. Then I'm going to pick a k. Now, if I like 2 a lot, I might think I want to pick 2 again, but try not to pick the same number twice in a problem because that'll obscure the difference. It'll hide the difference between the two variables. We don't want to do that because very often the question is testing us on the difference between them. So let's make our k something else. Let's make our k, I don't know, something else easy like 4. So our k is 4. And again, notice I'm putting a box around them, so later I can say in goes the box, out comes the circle. And now let's read this problem again with real numbers. I'm going to replace my k with 4. I'm going to replace my n with 2. Okay. If Leslie gives away 4 celery sticks, she will have half times as many as she had originally. So in terms of 4 and 2, how many celery sticks did Leslie have originally? So I want to know how many she had originally. And how will I know? Well, if she gives away 4, then she'll have half as many as she had originally. So originally, I want you to imagine that you have an unknown amount and you give away 4, and that just cut your stack in half. Now you have half as many. That must mean you had double that 4 before, which means we started with 8. So if I have 8 and I give away 4, I'll have half as many as I had originally. So I know the answer to this in real numbers is 8 when my n is 2 and my k is 4. And now I'll say it, in goes the box, out comes the circle. So I'm going to put my box numbers in. I'm going to put 4 in for k and 2 for n. Well, that's 4 plus 1/2. That's not going to be 8. That's just going to be 4.5, not this guy. This is going to be 4 times 2 plus 4. That's 8 plus 4. That's 12. That's not 8, so not that guy. This guy here is going to be 4 times 2 in the numerator and 2 minus 1 in the denominator. That's 8 over 1. That's 8. That works. We'll keep that one in. Now you might be thinking to yourself, Donna, do I have to try that last one if I know that it's C? And the answer is yes, absolutely yes. Here's the reason why. If you pick numbers that have special properties for a problem, there is a chance that you might get 2 answer choices that give you what you're looking for. That does not mean there are 2 right answers. That just means you got a little unlucky with the numbers that you picked. So no big deal. If that happens, listen to me carefully. Pick new numbers, try again. Literally just pick new numbers, try again. The chances that it'll happen again are pretty rare. If it does happen again, pick a different kind of number. Pick a negative number, pick a fraction, pick a negative fraction, pick something a decimal, something a little bit weirder. Yes, then the chances that it'll happen again will be pretty low. But for this one, let's just try that last one to make sure we didn't get 2 right answers accidentally. So we put a 4 in the numerator here and a 2 plus 1 in the denominator. That gives me that D would be 4 over 3. That is not the 8 that we're looking for, so we can cross that out. Check it out. We found the same answer without having to go through all that algebra. So again, remember the steps. Plug in for your variable. Do the problem with real numbers. Then once you've done the problem with real numbers, and you get the answer, plug the variables that you picked into the answer choices and see which one gives you the same thing. So now let's explore other forms of plug-in problems. So the one that we just did, you can notice we had multiple variables and we were able to pick them independently. They didn't influence each other. Here's another example of that. How many hours are there in D days and H hours? Now you might want to pause for a second and see if you can identify what it is that we're solving for and maybe give this problem a shot. So maybe try to pause the video here and see what you can do. So what we're looking for is how many hours there are in D days and H hours. Now, some people can do this algebraically. They're just like, oh, I think it's this one. But again, even if you do it algebraically, you might decide to check it with a plugin just to be sure. Now, also a lot of people will be like, what the actual heck is this problem asking me? So right away, we're gonna replace our variables D and H with real numbers. I'm gonna make D 2, because I love 2. and I'm going to make H 3 because that's nice and simple. So now the problem reads, how many hours are there in 2 days and 3 hours? Now what you'll notice is that the 2 and 3 don't really influence each other, so I can kind of pick them whatever I want. So how many hours are there in 2 days? Well, in 2 days, there's going to be 48 hours. And 3 more hours, well, I'm going to add 3 hours onto that. In 2 days and 3 hours, I have 51 hours. So now let's go to the answer choices and say, in goes the box, out comes the circle. 24 times 3 plus 2. Ooh, that's going to be way too big if I punch that out on my calculator. So not that guy. I believe that's 74. Yes, not that guy. This guy here is 3 plus 24 times 2. Well, if I punch that out on my calculator, that's 51. There we go. Here, this is going to be 24 times 3 plus 2. That's 24 times 5. Ooh, that's going to be way too big. Let's cross that out. That's going to be 120. No, it's too big. This guy over here, we have 3 plus 2 over 24. Well, that's just 3 and a 12th. That's going to be way too small. So let's cross that out. All right. We found our answer here. So again, this is an example like the last one we did with the celery sticks, where there are multiple variables, but they don't influence each other. Now I want to look at another one that has multiple variables that do influence each other. They are related. So take a look at this one. If x plus 5 is 3 less than y, then x minus 2 is how much less than y? Notice again, they're asking here for a relationship between unknowns. So while we don't see variables in the answer choices, they're asking us to relate together two unknowns. So what we can do here is plug in. Now you'll notice if I say, oh, I'm gonna make my x 2 and my y 3, that this actually isn't gonna work in this problem. Take a look. 2 plus 5 is 3 less than 3. Wait a minute, 2 plus 5, that's 7. Is 7 3 less than 3? No, 7 is 4 more than 3. So I must have mixed something up. The issue here is I picked my x and my y independently, when really whatever my x is will influence or dictate whatever my y is. So let me repick my y and say to myself, okay, if x is 2, if I decide that x is 2, that I picked randomly, 2 plus 5 is 7. Okay, and 7 is 3 less than whatever my y is. What is 7 3 less than? Well, 7 is less than 8 and 9 and 10, 11. So 7 is 3 less than 7, 8, 9, 10. 10. So we're going to say y is 10. Okay, so now we can do the rest of the problem with our real numbers. We can say x minus 2. X minus 2, well, that's 2. Is how much less than y? What was our y again? 10. So x minus 2, if x is 2, 2 minus 2, that will be 0. And 0 is how much less than 10? It's 10 less than 10. There we go. So we're going to go ahead and pick that as our answer. Now, will this work with other numbers that we pick? Absolutely, as long as we keep our relationship consistent. So let's try this with a totally different number. Let's pick something weird. Let's pick 17. What if x was 17? 17 plus 5? 17 plus 5, that's 23. And what's 23, 3 less than? Well, if I go up 3, 1, 2, 3, 23, 24, 25, 26, my y must be 26. All right, let's try it out. X minus 2 in this situation would be 17 minus 2, which would be 15. And 15, oh, sorry, that shouldn't be, that should have been 22, not 23. That's my bad. 22, and then we'd have 25. That's my bad. Well, we'll make our y 25. Now we have the right relationship. Okay, so to say again, our x is 17. Our y is 25. I just miscounted on that. I apologize. 17 minus 2 then would be 15. And 15 is how much less than our y, which was 25? Again, we get 10, because this question is not testing us on real numbers and the relationship between them. It's testing us on the relationship that they've set up between these two unknowns. So again, why we can plug in for one, solve for the other, and the relationship will be maintained. All right, let's look at another one. Now, you might have noticed that when we're working with plugin, we're working with a lot of variables. Variables in the answer choice, variables in the question stem. When it is a variable dance party, there's an excellent chance we're plugging in for that. Yeah? But we can also use this technique when we have what are called implicit variables, which are variables that you can't see. So we'll give or basically like unknowns that are worked into the problem. So I'm going to give this a read and let's see if we can see what's plugin-y about this, even though there are not a lot of variables or any variables at all. Larry cuts a piece of paper into 2 equal pieces. So let's give ourselves a piece of paper here. Boop. And he cuts it into 2 equal pieces. So let's do that. Then he takes one of those pieces, how about this guy, and cuts it into 3 equal pieces. All right, let's do that. The area of one of the smallest pieces is what fraction of the area of the original piece of paper? So they're asking me this little piece here is what fraction of the original piece of paper. Now, you might be able to eyeball this, but let's pretend like we can't. And we can say to ourselves, okay, how do I find this? They don't actually give me any way to find the smallest piece. They give me no dimensions at all. And they don't give me a way to find the original piece. Again, they don't tell me how big this piece of paper is. So it must not matter because indeed they're not asking us for either of those things. They're asking us for a fraction, and a fraction is a relationship between the part and the total. So in this case, the part would be the small piece and the total would be the original piece of paper. Yeah? So guess what we can do? Plug in for one, solve for the other, and see which one, and see what we get. So let's try that. Let's pick a random number for our little yellow piece, our small piece. Let's say it's 3. Well, that means this other piece would also be 3 because they're equal sides, and the other piece would also be 3. And then that whole half would be 9, which means the other half would also be 9, which means the whole darn thing would be 18. 9 plus 9. If we have 18 there, and I do the small over the original, the small is 3, the original is 18, that gives me 3 over 18, which reduces to 1 over 6. So again, not too crazy a problem, but again, to get the idea that they could be asking us for a relationship between unknowns. Let's look at a harder version where they're asking us for implicit variables. Scott drives to Bob's house at a speed of 30 miles per hour and drives back at a speed of 50 miles per hour. Let's go ahead and extract this information. Scott drives to Bob's house at a speed of 30 miles per hour. 30 miles per hour. I mean, each hour he goes 30 miles and drives back at a speed of 50 miles per hour. So every hour going 50, a little faster on the way back. If he takes the same route both ways, so he's going to take the same route. I'm going to draw myself a little highway right here so I can remember that he's going the same route both ways. Boop, boop. What was his average speed in miles per hour for the whole trip? Now, average speed, we have to be careful here. It's very tempting just to try to average the speeds, to take 30 and 50, add them together and divide by 2. That would give me 40, and everybody picks B and thinks they're done. But wait, we spent longer going 30 than we did going 50 because we were going slower to cover the same distance. So we can't actually weight our rates evenly when we spend more time doing one than the other. So please know average speed is not the average of the speeds. No, no, no. It's the total distance divided by the total time. You can only average the speeds if you're spending the same amount of time going both, which we're not doing here. So, question is, in this problem, did they give us the total distance? Give it a quick look. No, they didn't. Did they give us the total time? They didn't give us any time at all. So wait a minute, this is starting to look an awful lot like that problem that we just did that was asking us for a relationship between 2 unknowns. All right, no big deal there. We can plug in for one and solve for the other. So let's plug in for our distance. I'm going to pick numbers that make my life nice and easy. Yeah, if I pick 10, to go 10 miles at 30 miles an hour would mean it would take me less than an hour to get there. Now I'm working with fractions and that makes me sad. So instead, I'm going to pick a number that both 30 and 50 go into. I'm going to pick 150 miles. And again, if I picked 10, I could still do it. It just wouldn't be as comfortable. So if I'm going 150 miles at 30 miles an hour, figure the first hour I go 30, the second hour I go 60, first hour I go 30, the second hour I've covered 60, and then 90, and then 120, and then I'll get to 150 after 1, 2, 3, 4, 5 hours. Another way you could figure that out is the formula distance equals rate times time. So if our distance is 150 and the rate that we're going is 30, and we want to find how long that will take us, our time, we can just pop in our knowns to solve for our unknowns, divide by 30, and you'll get that t equals 5. So 5 hours to get there. And how long to get back? Well, let's see. We're going 50 miles an hour on the way back. So 50, then 100, then 150. Oh, it only took me 1, 2, 3 hours. Or again, if I'm using my distance equals rate times time, I would say my distance is still 150, but now my rate is 50 miles an hour. If I divide both sides by 50, 150 divided by 50 will let me know that my t equals 3 here. So that's 3 hours on the way back. So what is my total distance? Well, going there 150 miles and then coming back 150 miles, my total distance is 300 miles. And I'm going to divide that by my total time. Well, it was 5 hours there and 3 hours back. My total time would be 5 plus 3, which is 8 hours. When I go ahead and punch that out on my calculator, I get 37.5. Now, you might be thinking, well, Dawn, I kind of knew that. If the average was 40, if I just average them and I'm weighting this towards the 30, shouldn't I go lower? Yes, absolutely. But again, remember, I'm teaching you plug-in here, so you can keep an eye out for when they're asking you for a relationship between two unknowns that you can plug in for one and solve for the other. And a good takeaway from this problem too is that the average speed is not the average of the speeds, it's the total distance divided by the total time. All right, very good. So this works in geometry too. We do have to know a little geometry in order to be able to do this, which is if you have a straight line, the rotation from, if you have a vertex, from one ray to the other is going to be 180 degrees. So if I were to split that up into two angles, boop, boop, anyway, I like that, this angle here and this angle here would add up to be 180 degrees. So let's keep that in mind. So the question states, in the figure above, if y equals 90 minus x, what is z in terms of x? So what is this saying? What is z is what we're solving for. They're asking us, what is z? That's what we're solving for. We're solving for z. This language here, in terms of x, means we're going to express z using the variable x. We're going to say what z is, but we're going to use x in that saying of z. Whenever you see that, it's an excellent opportunity to plug in because you'll notice a bunch of variables in the answer choices. Yes? So if we're thinking about what we're going to plug in here, looking at this equation, we can see that our x is in an equation with y. So picking what x is will tell us what y is, and because that means our variables are related. So let's pick our x. If x is, I don't know, let's pick 10 for this one. It works nicely with 90. If I put 10 in for my x, that means that y is 90 minus what my x is, which I said was 10. So that would mean my y is 80. So I have my numbers that I picked. Let's put them in. So I have x is 10, y is 80, and I know that y plus z is going to add up to be 180. So if y is 80, that means my z would have to be 100 to make up the rest of the 180. Okay, now we're going to say it for ourselves. In goes the box, out comes our circle, the thing that we're looking for. So I'm going to put in 10 for my x, and I'm going to see which one gives me 100. So looking at A, I have 90 plus 10. That's 100. We'll keep that one in. Should I try the rest of them? Yes, we should. So just to make sure we don't get double right answers, so we say 90 minus 10, that's 80. Not that guy. This one here is 180 plus 10, that's 190, so not that guy. This is 180 minus 10, that's 170, so not that guy. Looks like we found it. All right, very, very good. So, lots of different opportunities. Let's have a little practice. I'm going to take you through this plug-in drill here, and that's where I'll end the video. And we'll pick up with another one for back solve when we're ready for a little bit more. All right, so let's read number 8. If P, Q, R, and S are consecutive even integers such that P is less than Q, is less than R, is less than S, then how much greater is S minus P than R minus Q? So let's go ahead and right away, let's plug in for our variables. But it's very important to pick numbers that match the restriction of the problem. They told us that P and Q and R and S are consecutive, which means one right after the other. Like Monday, Tuesday, and Wednesday are consecutive days, right? Consecutive, even like 2, 4, 6, 8, 10, not the numbers that are divisible by 2, and integers, whole numbers, no fractions or decimals, that P is less than Q is less than R is less than S. I have to make P the smallest one. Maybe I'll make that 4, and then Q would have to be the next consecutive, or the consecutive even, so that would be 6, and then R would have to be 8, and S would have to be 10. Now I've plugged in consecutive even integers where P is less than Q is less than R is less than S. And now let's figure this out. S minus P, what's that? Well, that's 10 minus 4, so that's 6. And R minus Q, that's 8 minus 6. 8 minus 6, that's 2. So how much greater is 6 than 2? Well, 6 minus 2, well, that tells me it's 4 greater. So my answer is 4 in real numbers. Let's go for the next one. Garth has X books, which is 20 more books than Henrietta has. Let's make that a little bigger. If Garth gives Henrietta 7 books, let's highlight, how many books does Henrietta now have? Well, let's plug in. I'm going to pick a number here greater than 20. Because say I picked that Garth had 5 books, and that's 20 more than Henrietta has, then Henrietta would have to have a negative number of books to make this work. So you know what? Let's make this 50 instead of 5. So Garth has 50 books, and that's 20 more than Henrietta has. So what is 50 20 more than? Well, then Henrietta must have 30 books. And if Garth gives Henrietta 7 books, Garth's going to give Henrietta 7 books. And we want to know how many books does Henrietta now have? Well, she had 30 and she just got 7. Let's give her 7 more books. She'll have 37 books. So that's the answer to the question. How many books would Henrietta now have when X is 50? So when I pop in 50 for my X, I want to see which one here will give me 37. So 50 minus 27, that's not what I wanted. That's 13. Let's cross that one out. 50 minus 20, that's 30. That's how many she had originally, but that's not what we're looking for. 50 minus 13, that's 37. We like that. 50 minus 7, that's 43, not what we wanted. So let's go with C. Ooh, now this next one has multiple variables. Let's ask ourselves, are these variables independent or are they related? Well, we can tell they're related because if I pick what A and B are, and I calculate that, that'll dictate what C is. So I don't want to pick C independently. I want to find out what C is based on what I picked for A and B. So let's plug in for A and B. And then we'll say that B, this means does not equals B. When B does not equal 0, then we want to know what 1 over B equals. Yes? Now you might be thinking, why did they tell me that B can't equal 0? Well, let's remember, if B is in the denominator and it equals 0, we would have something that's undefined. That's not allowed in math. So that's why they had to put this restriction that B can't be 0 in order for this problem to work. So let's pick some numbers. I want to pick something small for A because it's already raised to an exponent. So if I pick something too big, it's going to get really big really fast. So let's pick 2 for that. And let's pick 3 for B. Keep it nice and simple. So when I pop that back into my equation over here, I get A squared times B equals my C. So I'm going to put a 2 in for my A and a 3 in for my B. And I'll get 4 times 3 equals 12. Oh, so it looks like my C should be 12. Let me box up the numbers that I picked here. Picked and solved for, really. And let's see, what is it that I'm solving for? I want 1 over b. 1 over b, in real numbers, that my b is 3. So in real numbers, it would be 1 over 3. That's what I'm looking for. So in goes the box, out comes the circle. I'm going to put 2 and 12 into the answer choices and see which one gives me 1/3. So this is going to be 2 squared times 12. Oof, that's going to be too big. That's not going to be 12. That's not going to be 1 over 3. This one here is going to be 2 squared over 12, or 4 over 12. Well, that reduces to 1 over 3. So let's keep that one in. This guy here is going to be 12 over 2 squared. So 12 over 4, that's 3, not 1/3. So we'll cross that one out. And then this guy here will be 1 over 2 squared times 12. Ooh, that denominator is going to get real big. That's going to be 48. 1 over 48. That's going to be way too big. So let's cross that out. Or way too big in the denominator, making the whole fraction way too small. So we're going to go with B on this one. All right, number 17. A number P is divided by 3, and the result is increased by 3. This result is then multiplied by 3. Finally, that result was decreased by 3. In terms of P, what is the final result? Well, if the first thing we're doing is taking that P and doing stuff to it, let's plug in for P. And if the first thing that we're doing to it is dividing it by 3, let's pick for P something that's easily divisible by 3. I'm going to go for 6. 6 can be divided by 3. So if I take 6 and it's divided by 3, I'm going to get 2. And then the result is increased by 3. So I'm going to increase it by 3, and I'm going to get 5. And then this result is multiplied by 3. So I'm going to multiply it by 3, and I'm going to get 15. And then finally, the result is decreased by 3. So let's decrease that by 3, and we're going to get 12. So that's our final result. That's what we're looking for. So we're going to circle it up, put a box around the numbers that we picked. In goes the box, out comes the circle. Well, this is just P, so that's just 6, not 12. This will be 6 plus 6, that's 12. Keep that in. This is 6 minus 6, that's 0, not that guy. This is 3 times 6 plus 6, that's 18 plus 6, that's 24. That's way too big. Bye-bye. And our answer is B. I'm going to go ahead and skip 18 for now. We'll come back to that on another day. Let's go for 21, yes? Hot dogs cost $H each, and pretzels cost P each. How much would it cost in dollars to buy H plus 1 hot dogs and P minus 1 pretzels? How much would it cost in dollars to buy H plus 1 hot dogs and P minus 1 pretzels? So let's plug in for our variables right away. I'm going to say H is 5 and P is 6. Okay, so hot dogs cost $5 and pretzels cost $6. Now, do they have to influence each other? No, it looks like we could pick these independently. Yeah, they're not stated as a relationship, so we can keep them just like that. Now let's ask ourselves the question, how much would it cost in dollars to buy 5 plus 1 hot dogs and 6 minus 1 pretzels? Well, I don't normally buy 5 plus 1 anything. I normally say 5 plus 1. 5 plus 1, that's 6. So I'm going to just replace that with 6. Hot dogs and 6 minus 1. 6 minus 1, that's 5. 5. Okay. So now I'm going to read this problem again because that was a little confusing. Hot dogs cost $5. So hot dogs, they cost $5. I said that. And pretzels, they cost $6. How much would it cost to buy 6 hot dogs? I'm buying 6 hot dogs and 5 pretzels. Well, if hot dogs cost $5 and I'm buying 6 of them, that will cost me $30 just for the hot dogs. And if pretzels cost $6 each and I'm buying 5 of them, well, that would also cost me $30 just by multiplying them together. So if I add those together, it's going to cost me $60 to buy 6 hot dogs and 5 pretzels. So the answer I'm looking for is 60, my H is 5, and my P is 6. Now, if I'm looking at answer choice A, that would be 5 plus 6. Oh, that's just 11. That's not what I wanted, right? And then let's see, we can do in our calculator, 5 times 6, that's 30. minus 5, that's 25, plus 6, that's 31, minus 1, that's 30, but we wanted 60, so not what we're looking for. This one here is 5 squared plus 6 squared, that's 25 plus 36. That's gonna be 61, a little too big, so not that guy. Now let's see this guy. Oh, sorry, I should have crossed out A. This last one is going to be 5 squared, 25, plus 6, 31, plus 6 squared, 36, minus P, which is 6, right? So let's punch that into our calculator. 25 plus 6 plus 36 minus 6. Ooh, you know what I did? I put in a 6 instead of a 5. I needed a 5 right there. Do you see that? That was a mistake on my part. Should it look more like this? Yeah? So we have 25 plus 5 plus 36 minus 6. And that's what will give us 60. So that's our answer. A bit of a tricky one, but I think once we replace the variables with real numbers, it's a lot easier to see what we're doing. So next one, the sum of 3 consecutive integers is S. Sum means we're adding 3 integers that are one right after the other, and that's going to give us S. So I think we should plug in for our integers. Let's plug in, 2 and 3 and 4, because we're avoiding 1, 0, and negative 1. So that makes it available for me to see that my S would be 2 plus 3, that's 5, plus 4, that's 9. So my S is 9, and you'll notice that's the variable I need for my answer choices. What are we solving for? What is the greatest of these integers in terms of S? Again, now that we have our S, the greatest of these integers, what is that? What integers? Oh, the integers I picked. Which one's the greatest? 4. So I'm looking for 4. In goes the box, out comes the circle. Put in a 9, get out a 4. Well, let's put in 9s for my S's here. 9 over 3, well, that's 3. 3 minus 1, that's 2. Not that guy, I'm looking for 4. This is 3. 9 divided by 3 is 3. Not what I'm looking for. 9 divided by 3 is 3 plus 1. That's 4. I'll keep that one in. 9 divided by 3, that's 3. Plus 2, that's 5. Not what I wanted. There we go. Now this guy, we can see our variables are related. Check this out. If t does not equal 0 and s equals 1 over t, which of the following must be true? Okay, must be true. Whenever you see this, sometimes we'll have to try more than one option. But take a look here. If I say that t is 2, that actually dictates that my s equals 1 over 2. So with a quick little plug-in, let's see which answer choice might be able to be eliminated. So is it true that s is less than t? Yes, 1/2 is less than 2, so we'll keep that one in. Is s greater than t? Is 1/2 greater than 2? No. Now, this is s times t. That's 1/2 times 2. That's going to be 1. Is 1 greater than 1? No, let's cross that out. Is 1 greater than 0? Yes. Ooh, I'm so glad we tried all our answer choices. So let's pick new numbers, try again. Let's say t is 5. So s would be, t is 5, s would be 1 over 5. Okay, let's try. Again, I don't have to try b and c again. I already know that those don't work. Is it still true that s is less than t? Yes, 1/5 is less than 5. Is it still true that s times t is greater than 0? Well, let's see. 1/5, that's our s, times our t, which is 5. That's still 1, so yep, still greater than 0. Remember what I said, when you get the same kind of answers again and again, pick something weird. So let's go not for a positive, let's go for a negative or 1 or 0 or -1 or something like that, or even a fraction. Let's try -2. What if I made t -2? Let's try that. That would mean that s is -1/2. Oh, this changes the game a little bit, because what do you notice? Is it still true that s is less than t? Well, if I look at my number line, here's 0, here's -2, here's -1. -1/2 would be here, and -2 would be here. -1/2 is greater than -2, so that invalidates A. Now, is it still true that negative 1/2, my S, times negative 2 is greater than 0? Well, yes, a negative times a negative will always be positive, and 1/2 times 2 is 1, and 1 is greater than 0. So we found out that ST is greater than 0. Answer choice D is our answer choice, but we did have to get a little creative about what we plugged in. All right, for our last one here, we see W. Decreased by 40% of W yields X. X increased by 50% of X yields Y. Y decreased by 10% of Y yields Z. According to the information above, Z is what percent of W? So here we can notice that our variables are related. We're taking our W, we're decreasing it by a certain amount, and it yields or equals X. Then we take that X that came from our W, increase it, and it gives us our Y. And then we take that Y and we decrease it, and it gives us our Z. So basically we're taking our W, making it bigger, making it smaller, making it bigger, making it smaller, and then that turns into our Z. So if I pick my W, that can help me find my Z. Now my W, I'm gonna pick anything I want in the world. I'm not gonna pick 3, because finding 40% of 3 sounds a little bit annoying. Much, much better. Let's pick 100. 100 is always great to use for plugging in with percents, because percents are always out of 100. So if my W is 100, I'll take my 100. I'll decrease it by 40% of, which is multiplication, my W, which was 100, and that will yield or equal my X. Now I can grab my calculator and punch that right in, and I'll find out that that's 100 minus 60, which gives me that my X equals 40. I'm gonna box my variables there. Then I'm gonna take that 40, I'm gonna take that X, and I'm going to increase it by 50% of 40. Well, you might know that 50% of 40 is half of 40. That's 20. If I increase 40 by 20, I get 60. But let's show the math. 40 increased by 50% of 40 yields my Y. So again, that'll be 40 plus 20 if you punch it out on your calculator, and that'll give us Y, which is 60. And then let's take that 60, and we're gonna decrease it by 10% of 60. And that's going to, oh, wait, did I do something funny there? Oh, I so did. Guys, I apologize. It's been a long video. Let's take this back a little bit. Did anybody catch my error? Did anybody catch it? Did you see what I did there? This is actually what this is. Yeah? 60 is what it would be. I just swapped the numbers here. Let's go ahead and take that back a little bit. Ooh, Donna, I gotta fix that. All right, so we're gonna take that 100. Let's take it back from the top, yes? We put in 100, and we're decreasing it by 40% of 100. And again, if you pop that into your calculator, you'll get 100 minus 40, because 40% of 100 is 40, and that'll give us our X, which is 60. Then we'll take that 60 and increase it by 50% of 60. That'll give us our Y. We're gonna take our 60 and increase it by 50% of 60. 50% of 60 we know is 30. So 60 plus 30, that's gonna give us our Y. So we found out that our Y is 90. And then we take that Y, we take that 90, and we're going to decrease it by 10% of 90, and that's gonna give us our Z. So 90 decreased by minus 10% of 90, and that gives us our Z. So that's 90 minus 9, that gives us that our Z is 81. And then it asks us, Z is what percent of W? 81 is what percent of our 100? Well, 81 is what percent of 100? 81 is what percent of 100? Well, that looks like 81% to me. And you can see now why it was so nice that we picked 100 to begin with. So thank you so much for hanging in there with me for this plug and drill. We'll come back in our next video for back solve, and then we'll do the mixture one all together.